Hey everyone, welcome back to the CyberNetters Networking 1 course. I'm Andrew Yick, and today we're moving up the stack to one of the most critical components of networking, the network layer and internet protocol, also known as IP. The network layer is responsible for making sure data gets from one host to another, even across different networks. Unlike the data link layer, which focuses on local point-to-point connections, the network layer ensures end-to-end communication, which routes packets across multiple hops to reach their destination. So in this video, we will cover how IP addressing works, the IPv4 versus IPv6, this subnetting and hierarchical addressing, the routing and gateways, and the address resolution. By the end of this video, you have a strong understanding of how packets move across the internet, how devices are assigned addresses, and how networks are structured for efficient routing and communication. Let's dive in. As we discussed in the communication models video, the network layer is like a GPS. It doesn't deliver data directly like the data link layer, but what it does is it figures out the best route for data to travel, and it makes sure that it reaches the right destination, even if that means crossing multiple networks. So, what is happening at this layer, you may ask? So, the data at this layer is called packets. So, think of them like postcards that carry information, but it relies on the network layer to find the best delivery path. Some of its most important responsibility is that it's responsible for the communication between devices on different networks. It uses IP addresses to senders and receivers, and it finds the best path for data to travel. So let's take a deeper dive into the responsibilities on the network layer and its role in the packet delivery across networks. So first of all, it addresses packets with an IP address. So like each packet is assigned a source IP address, which is simply where it came from, and a destination IP address where which is going. And then this makes sure that the data reaches the correct devices and across networks. So, for example, your computer with the IP 192.168.110 can send a request to 8888, which is Google's DNS. And the IP address identifies where the request is going. And then second, it encapsulates the packet. The network layer adds an IP header to the data received from the transport layer, which is the TCP UDP segment. So, for example, when you send an email, it is encapsulated in multiple layers before it's transmitted. It then routes the packet to the destination. So, routers use the IP address to determine the best path of the packet to travel. If the destination is on a different network, the router then forwards it using the best available route. So, for example, if you're accessing a website hosted in another country, your data travels through multiple routers across the internet before it reaches its destination. And then it decapsulates the packet, which means that when the packet reaches its destination, the IP layer removes the network layer, sorry, removes the IP header. The data is then passed onto the transport layer, which ensures that it's delivered correctly to the intended application. So let's say your device receives a web page from the server. The network layer strips the IP information and then hands the data to the application layer or the web browser to display the content. So let's talk about IPv4. So some of the things about IPv4 that we'll be diving deeper into is that IPv4 is connectionless and reliable because it uses the best effort delivery, which is not the most reliable method, and also IPv4 is media independent. So IPv4 is connectionless. What that means is IPv4 does not establish a dedicated connection before sending data. Each of the packets are independent, meaning there's no guarantee that the packets would arrive in order or even at all. So if reliability is needed, instead of using this connectionless communication, higher layer protocols like TCP will handle the retransmission ordering. So, for example, think of it as like sending a letter without calling the recipient first. You just mail it and then you hope it arrives. So let's talk about a bit about the best effort delivery, which is unreliable as mentioned earlier. So IPv4, as we mentioned earlier, does not guarantee packet delivery, order, or duplication prevention. So what happens if a packet is lost? Well, it is not automatically resent, which unlike TCP, which can request retransmissions. The reason why you might be wondering why it's called best effort is because the IPv4 tries its best to deliver the packet, but it doesn't check to see if it made it. So think of it like a postal service route tracking. So you send a package, but there's no guarantee it arrives or in what order it gets delivered. So what does it mean to be media independent? So IPv4 does not depend on the type of network medium, such as wired, wireless, fiber optic, etc. It can like deliver stuff over any type of network medium. It can also work over any physical network just as long as it can carry IP packets. But some network types have different MTUs, also known as maximum transmission units, which can affect how large packets can before fragmentation occurs, which we'll be going more into depth in the next slide. So think of this as like a message that can be sent by email, mail, radio, or text. The message remains the same regardless of how it is delivered. So, what is the MTU or the maximum transmission unit? So, it is simply the largest size of a data packet that can be sent over a network without fragmentation. It is measured in bytes and it varies based on the network type. So, what happens if like it is larger than the MTU? So, if a packet is larger than the MTU, it must be fragmented into smaller pieces, which can then slow down communication. A larger MTU reduces the number of packets sent, but it increases the risk of errors if a packet is lost. However, a smaller MTU reduces the chance of fragmentation, but it increases overhead because more packets need to be sent. So, what are some common MTU sizes for different networks? So, for example, the Ethernet could have a typical MTU size of 1500. A IPv6 can have a typical MTU size of 1280 bytes, and then a wireless can have 2304 bytes. Okay, so I'm not going to go super detailed in this slide, but I want to show you how an IPv4 packet header is like. So some things I want to point out is the time to live, which is why it can only live so long, which TTL is basically the maximum hops before it's undeliverable. So these packets are not like permanent, but rather it like dies after a certain amount of hops. And then 254, which is the fourth byte, is the outer edge of the router. Also, since, as we mentioned earlier, network layer is unreliable in terms of error checking and detection, it uses the layer 2 and 4 for reliability. And then also, the IPv4 packet header, as you can see, is made of 32 bits or 4 bytes. So there's 8 bits in a byte, so 4 times 8 is 32. So let's talk a bit about how IPv4 addresses are structured and represented. So as you can see, IP addresses are 32 bits long, and they're divided into 4 groups of 8 bits. These are called octets. Each 8-bit group can hold values between 0 to 255. For example, a binary representation can be shown there. And then when it's converted into decimal, it can display something like 131, 108, 122, and 204. So basically, when you see an IP address, it's a computer reads it as 0 to 1s rather than the ones you can see on screen. So basically, why use the decimal dotted decimal notation? So as I mentioned before, computers use binaries, but humans, it's part of human nature when they find it easier to read decimal numbers. So The binary address is split into 4 octets, and each octet is converted to decimal and separated by dots. So for example, there's 192.168.1.1, which is an example of a dotted decimal notation. So let's talk about how an IPv4 address is structured. So as we mentioned earlier, IPv4 address is 32 bits long and it's divided into 2 parts, the network and the host number. So the network number identifies the specific host. All devices in the same network share this part. So let's say our example of an IPv4 address is 192.168.1.5, assuming a /24 subnet. So let's say the network part is 192.168.1. So then 192.168.1 would be the same for all hosts in the network. And then let's talk about a host number. The host number identifies the individual devices or hosts within the network, and each device has a unique host portion. So let's say the host part is 5. So only that device would be unique in terms of having 5 as their unique identifier, and no other devices will have 5. So why is this important? So routers use only the network number to forward packets, and it makes routing more efficient. So basically, the router will only need to know the network half and not the address of the individual half. So the subnet mask determines which part of the IP address represents the network and which part represents the host within that network. It does so by using binary numbers. So the ones in the subnet mask represents the network portion, and the zeros in the subnet mask represents the host portion. So as you can see in the 255.255.255.0 subnet mask, the first 3 octets, which is the first 24 bits of the subnet mask, are all ones and binaries, which means the first 3 octets of the IP address belong to the network, and the last octet, which is the host portion, is zeros, meaning it's used for devices within the network. So there's 2 ways to represent a subnet mask, which is the traditional decimal method and the CIDR, which is the class's inter-domain routing notation. So basically, the subnet mask, as we mentioned before, is written into dotted decimal format, which shows the part of the IP address that belongs to the network and which part belongs to the host. So as we mentioned before, for the IP address 255.255.255.0, the first 3 octets, the first 24 bits are for the network, and the remaining 8 bits are for the host in the network. This method is known as classful routing, which the default subnet masks are assigned based on the address classes A, B, or C. And then we have the CIDR notation, which basically means writing the subnet mask as a prefix of the IP address. So instead of writing 255.255.255.0, we write 192.168.1.2./24. So the /24 means the first 24 bits are for the network and the remaining 8 bits are for the host portion. So there's 2 main types of addresses used in networking. The first one is the MAC address, which is a layer 2 address, and then the network address, which is a layer 3 address, or also known as kind of like an IP address. So the MAC address is like the physical address of the device. It is burned into the network interface card, or NIC, during manufacturing, and it cannot be changed. It is also used for communication within a local network, or LAN. It also operates at a layer 2 or data link layer. So for example, let's think of it like a home address that never changes. And then you have the network address, which is our logical addresses assigned by network administrator or dynamically via DHCP. It's also used to identify devices across network, and it operates at layer 3, and it can change depending on the network the device connects to. So for example, like a mailing address that changes when you move. So let's talk about a bit about the role of a default gateway in a network. So what does a default gateway do? It is the IP address of a router that allows devices on a network to communicate with devices outside of their local subnets. So, for example, if a computer with IP of 192.168.1.2 wants to communicate with AAAA, which is Google's DNS server, it needs to send traffic to its default gateway, which is 192.168.1.254, and then it forwards it to the destination. Okay, so let's try to dive deeper into a role of a gateway in routing. So, routers must know where to send the packet or else it gets dropped. Each packet arriving at a router's gateway interface is checked against a routing table to determine its next hop. And if a network is not directly connected, the router forwards packets to the next router, which is also known as the next hop. So as you can see in the diagram in the top right, there's two routers, which is the local router and the remote router, which are shown. Each router has an interface on the 192.168.1.0/24 network which connects them. So as you can see, the local router has a routing table as shown in the image. The traffic for 10.0.1.0/24 and 10.2.0/24 is sent to 192.168.1.2, which is the remote router. Then what does a remote router do in the case? It delivers the packet to the correct destination network. So how I like to think about it is using a package delivery system. So think about how you're mailing a package to another city. The local post office, which is the router in this case, checks its routing table to see where the package should go. If the package's destination is not in the local city, it gets forwarded into a regional hub, which is the next hop router. And then the regional hub then forwards the package to its final delivery location. So let's now talk about how routers determine the best path to send packets using your routing table. So as you can see, a snippet of an IP route, basically the destination network is shown in red. What this means is it's the final network where the packet needs to go. So in this case, 10.1.2.0 would be the destination network. And then you have the metric, which is green, which is the value that helps determine the best route when multiple paths exist. So a lower metric means a better route. So for example, 120/1 means a metric of 1, which is low, which means this route is preferred. And then you have the next hop, which is in blue, which is the next router or gateway that will forward the packet to the destination. So what this means right here is that the packet will be sent to 192.168.2.2, which is the next hop. So let's now think of it as like a metaphor. So how I like to think of it is a highway navigation. So the destination network is the city that you want to visit. The next hop is the nearest highway entrance, and then the metric is the number of tolls or traffic conditions that determine the best route. So let's talk about the concept of address resolution. Address resolution is the process of mapping a high-layer address like an IPv4 address to a hardware address, like a MAC address. This is important because routers and switches need to know both the logical IP address and the physical MAC address of a device to successfully forward packages. And then we have the ARP, which is also known as the Address Resolution Protocol. So what ARP is it's the protocol to map an IPv4 address to a specific MAC address. So let's talk about the ARP process. So when a device, like a computer or router, wants to send a packet to an IP address, it does not know the MAC address of the destination. So it sends a ARP request to the network saying like who has IP address XXXX. So the ARP response could be the device with the IP address in question will respond with the MAC address. I have an IP address of XXXX and my MAC address is so on and so forth. This response allows the device to map the IPv4 IPv4 address to the MAC address and use it for communication. So if you think handling 32 bits is a lot, think about handling 128 bits now. So as you can see here, this is the IPv6 header. So some things I like to point out is that the header length, ID, flags, fragment, offset, checksum, and padding are removed here in the IPv6 header, and it's a fixed length header, which is only 2 times the IPv4 header. So fragmentation here is highly discouraged of IPv6. It is to use a MTU detection algorithm for the smallest MTU across the entire transport path. So think about what we would do with no checksums. So let's talk about how IPv6 addresses are formatted and how they can be condensed for easier readability. So, as we mentioned earlier, the IPv4 uses the dotted decimal notation in order to display the IPv4 address. So, like for example, 127.54.83.21. But here in IPv6, we uses the colon hexadecimal notation. So unlike IPv4, which uses 4 decimal numbers, which is 32 bits, IPv6 has 128 bits and is represented in 8 groups of 4 hexadecimal digits. So here are some rules for condensing an IPv6 addresses. Since IPv6 addresses, as you know, can be long and repetitive, we use these 2 key rules to shorten them. So the first rule is to skip leading zeros. So each tuple, which is a group of 4 hex digits, can have leading zeros omitted. So as you can see in the example on the screen, zeros before a number in a section can be removed. So 0020 becomes 20. Rule number 2 is to compress a continuous zero block. So if an IPv6 contains a sequence of consecutive zero blocks, you can replace them with the 2 colons, but it can only happen once per address. So as you can see in the image, the double colon replaces the longest sequences of consecutive 000 groups. Thank you so much for watching. If you have made it this far, I truly appreciate your time and attention. If you found this video helpful, don't forget to give it a thumbs up and feel free to subscribe for more content like this. Do you have any questions or feedback? Drop them in the comments. I'd love to hear from you. Until next time, keep learning, stay secure, and I'll see you in the next video. Bye bye.